Thanks for having me here. Thanks for the invitation. And I'm gonna talk about various aspects of a silly-sounding problem. How should we estimate the mean of a random variable? Okay, this sounds super basic, and I was actually surprised to realize that not everything is understood about this really fundamental problem. We even wrote several papers on this, and then these are various co-authors: Christian Brownlees at my department, Luc Devroye at McGill, Emilien Joly, who was a PhD student who should be arriving here, Matthieu Lerasle, he's in Nice, and Roberto Imbuzeiro Oliveira, he's in IMPA. Okay, so this is the problem. We have n independent, identically distributed random variables, real-valued random variables, and we want to estimate the mean of these. Okay? So what would you do? Calculate the empirical mean, right?
Are they bounded? Or
huh?
Are they bounded or not?
If they were bounded, then my talk would be over very quickly. Okay? Actually, thank you. But actually, even in that case, it's I could a large part of the talk is even in that case makes sense. Okay, well, I'll get back to that. So, in general, they are not bounded, and then we know that if the x has a finite variance, then this has a very nice sub-Gaussian behavior. Okay, I just put just an upper bound form of it. Right, this is somehow an upper bound for the tail of the normal distribution. Okay, so if we scale by square root of n, then the difference between the empirical mean and the mean, the probability that this scale difference exceeds the standard deviations times something that scales with the square root of the log 1 over delta, that's gonna be less than delta. Okay, now the question is, well, this is of course asymptotic in nature. So the question is, under what circumstances can we get non-asymptotic inequality? So I would like to remove this limb here. And the question is, what can we do? Okay? All right. The nice thing in the central limit theorem is that it only requires finite variance and nothing else. And it's also nice. Okay, this is coming up. Okay. Now, if the distribution is sub-Gaussian, meaning that the moment generating function is bounded by the moment generating function of a normal random variable, and I should have written. Sorry, this should be centered. The moment generating function, this x minus the expected value, is bounded by this. Then this is actually non-asymptotic. Okay, and that's very easy to see by Chernoff bounds. Okay. So in that case, the picture is very nice and very clean. If we have sub-Gaussian random variables in this precise sense, then the central limit theorem is actually not only true in the limit, but for each n in this sense. Okay. The empirical mean, of course, is very attractive because it's very easy to compute. It doesn't require any previous knowledge of the distribution. Or of the variance, it scales automatically. So from a computational point of view, this is very nice. However, if the distribution is not sub-Gaussian, and we don't know what the distribution is usually in advance, then it's not clear what we can say. What's clear is that we still have Chebyshev's inequality, which has this form. It looks very much very similar to what we are hoping for, except that instead of that square root of log 1 over delta, we just have a square root of 1 over delta, which is an exponentially weaker bound in a sense. Okay, and this is especially hurtful when, like in machine learning, when we want to estimate the means of not just one random variable but lots of random variables simultaneously, and want to use some kind of a union bound. So it would be really important to actually have logarithmic dependence on 1 over delta. Okay, so Chebyshev's inequality doesn't give us that, and the bad news is that Chebyshev's inequality is actually tight. You cannot improve that in this precise sense. So there, in a very nice paper of Olivier Catoni, it's shown that no matter how, but n and delta are, there's always a random variable such that this inequality is tight up to this constant factor. Okay, so the empirical mean is no good in this sense. All right. So the question is, are there other estimates that behave better somehow? And under what condition are there sub-Gaussian estimates of the random of the mean? Okay. So here's the statement a little bit more formally. So if we have a class of probability distributions on the real line, and let's assume now that they have a finite variance, and I will come back to this assumption a little bit later. Does there exist a mean estimator? A mean estimator is just a function of our n data points. Does there exist such a function such that no matter, for all distributions in this class, with probability at least 1 minus delta, we have this sub-Gaussian bound? Okay? And now I allow this constant to be not square root of 2, like in the Gaussian case, but I'm happy to let it depend on the class. Okay? All right, so this is the question. For what kind of classes of distribution can we construct such estimates? Okay, and how? So far, so good. Okay. So one idea that practitioners use and that has been around in the statistics literature is truncate, simply truncate. If we suspect that we have a fat tail, then we will have so-called outliers. Then let's just forget them. So let's just look at, let's just throw out all values that are greater than some threshold b. Okay, and let's calculate the empirical mean only on the rest. Okay. Now there's a two-line analysis here. The details are not important. Basically, it says that if these guys become bounded, so we can use exponential concentration inequalities like Bernstein's inequality, and we get something that looks, and if we set this thresholding value b to be something that depends on delta and depends on an upper bound on the second moment, then we get something that looks sub-Gaussian. But it is not sub-Gaussian because this u is not the variance. This u is an upper bound for the second moment. Okay. So, the disadvantage of this method, there are various disadvantages. First of all, this is not a translation invariant estimator. Right? By truncating, we somehow imagine that the center of the universe is the origin, and we have no reason to assume that. So this is not translation invariant. It is not sub-Gaussian because the deviations don't scale with the variance or with the standard deviation, but they scale with the square root of the second moment. And if we are far from if the origin is far from the true mean, then this will be horrible. Okay. And also where to truncate? Well, that depends on this value, which we don't know, and it also depends on delta. Delta is the confidence parameter, right? That we want. Delta in this entire talk will come up on every slide. It's always the probability with which we allow the estimator to be off. Okay. So this I will just forget the truncated empirical mean because we can do much better. All right. So here's a conceptually beautiful mean estimator that actually has been around without making too much noise. It appears in at least, I found 3 papers in which this estimator comes up, but it was always just a little tool for particular needs in these papers. The idea is really simple. Let's do the following. Let's chop up the data into blocks, into independent blocks. And in each block, let's say of size capital N, in each block, let's calculate the mean, okay, the empirical mean, and now take the median of these values. Okay? Now this is not an unbiased estimate. Okay, so if you take the expected value of this, then it's not going to be the mean. However, it has this beautiful property. So if we choose the block size, capital N, to be n divided by log of 1 over delta, okay, delta is the same delta as before, then we have a sub-Gaussian upper bound. And this is true for all distributions with a finite variance. And you see this has the same the required form. It's 8, not square root of 2, but 8 times sigma times square root of log 1 over delta over n. Okay? And then this is non-asymptotic. Okay? Proof. This is the proof, really easy. By Chebyshev's inequality, each mean is within this distance, right? With probability 3/4. Okay? With Chebyshev's inequality gives us a weak bound. The dependence on delta is not the right one, but otherwise it has the right form somehow, the right scaling with the sample size. So each of these means are within this distance with the correct probability, with probability at least 3/4. So now what's the probability that the median is not within this distance? Well, that's going to be exponentially small, right? Because for the median not to be there, it must be that a binomial with parameters k is the number of blocks, and 1/4 is bigger than k half. Okay, but k was log 1 over delta, right? And this is exponentially small in. So this is going to be delta, and this guy is just this bound. Okay, so this is really simple, conceptually very simple and really nice. This always works, always. Okay. All right. So these are the good properties. It scales automatically with sigma. Well, of course, it has sub-Gaussian deviations. However, the parameter again depends on delta. Okay, so that's not so good, right? The number of blocks is like a constant times log 1 over delta. Yeah.
So you want something oblivious to delta and have the same thing independent of delta. That's what you want.
Sorry.
So you want to have an estimator that's like the same independent of delta.
This is coming up. Yes. Of course, it would be nice to have an estimator that works for all that, like the empirical mean. The empirical mean doesn't need to know the confidence level that we need. Okay, so this estimator does need that, okay. And there has been some work on generalizing this to various scenarios, using it for linear regression, for estimation in high dimensions, and so on. It's also nice that this estimator works even when the variance is infinite. Okay, so if we have a 1 plus alpha moment where alpha can be anything positive, less than or equal to 1, then it will give you something. It's not gonna give you 1 over square root of n scaling. It only gives you 1 over square root of n scaling if the variance is finite. But if the variance is infinite, then we get something. We get something. Okay? It turns out, I will mention this later, that this is the best you can hope for. Okay? So it will scale with this 1 plus alpha central moment in the correct way. Okay? So the median of means estimator is a very nice, very powerful estimator. Here's another one. This was introduced by Olivier Catoni. His idea was the following. So if the empirical mean, you can think about it as the solution of this equation, right? We calculate the value of mu for which this equation equals 0. Okay. Now he says, okay, so let's put in some function here that somehow chops off the tails in a nice way, and this particular form turns out to be important. Okay, so this phi function looks like looks something like this. Right? It's symmetric around 0, and it's nicer than it. It's symmetric. It's unbounded. Okay. This guy. All right. So for large x, it's like log 2x. All right. And he said, okay, so let's solve this equation. Let's find the mu for which that satisfies this. Okay. And here's the performance bound for any. So if this estimator will, I didn't tell you what this alpha is. You see, there's a scaling alpha here, which is a parameter of the algorithm. So this will have to be chosen in a correct way. And Catoni's result says that if we know an upper bound for the variance, then we can choose alpha to be of this form, square root of 2 log 1 over delta divided by n times this estimated variance. And then we will get something which is exactly of the right form. Well, this is not so important here, but this is exactly sub-Gaussian bound, even with the correct constant. Okay? And you can also choose if alpha in a delta-independent way, but still assuming a knowledge of a good upper bound on the variance. And then you get something which is not quite sub-Gaussian, but it's sub-exponential. So instead of the square root of log 1 over delta, we have just log 1 over delta here. So this, if we use this delta-independent choice of the parameter, then we still get exponential tails and the correct scaling. Okay. Okay, I guess this is what I just said. So it has sub-Gaussian deviations with optimal constants. This is really good. It scales correctly with the variance, except that it requires a knowledge of the variance, which, of course, you can try to estimate, and then that's a different section in Catoni's paper of what you can do in that case. However, it works only for finite variance. The finite variance is important. You can try to modify the estimate, but somehow you don't get the nice constants anymore. And again, the estimator, if you want truly sub-Gaussian performance, then it will depend on delta. Yes?
So is the advantage over median of means just the first bullet?
It's
both of means and delta?
Yes and no. So yes, at this level, yes. But then it turns out, and I will see if we can get to the very end of my talk. In some applications, this actually is better in a sense that when you want to estimate not just one mean, but lots of them. So you want to do empirical risk minimization. Then the median of means estimator is very difficult to handle, and this one you can do chaining and stuff like that. So in some applications it turned out to be better, but yeah, at first sight this seems to be the only advantage. Exactly. Okay. Oh, and also this last point is an advantage, that if you're happy with just sub-exponential bounds, then you can tune it without knowing delta. There's a single estimator that works for all confidence levels. Okay. So here's the proof of Catoni on one slide. It's wonderfully simple. So let's look at this function. Okay. Remember, this is the thing that we set equal to 0. Okay. So that's this curve. Right? It's a function. This should be m here. So it's a function of m, and at some point it crosses this line, and that's going to be our estimate. Okay, it's a decreasing function because phi is increasing. Okay, it's a decreasing function of m, and then for any fixed m, okay, we can calculate we can just write down the moment generating function of this random variable. Okay? And because of the specific form of this function, you can see that this is bounded by the exponential of this quadratic function of mu minus m. Okay. And then you use Markov's inequality, and what you get is that this Rm, this random variable, is bounded by this parabola. Okay? And now you do the same for minus R of m, and then what you get is that this function is lower bounded by this parabola. Okay? Therefore, the solution must be between these points, these 2 points. So you just have to solve where these parabolas cross this axis, and you get your bound. Okay? Really nice, really beautiful. Okay, so that's Catoni's estimator.
What's the computational complexity of actually finding?
Sorry?
What's the computational complexity of finding the mean?
The computational complexity. Yeah, that's a good question. Yeah, no. Actually, it's a convex optimization problem, because you can write down this as minimizing the function whose derivative this is. Okay, so it's a convex optimization problem.
It's also isn't it a binary search?
You cannot do with binary search. So in one dimension, this is not too bad, I think. It can be done. Okay. So why sub-Gaussian? Why are we so interested in sub-Gaussian? Well, in a sense, this is the best one that we can hope for. Okay. So there are a few facts here. So if no matter what we do, for any estimator, there exists a distribution whose 1 plus alpha's moment equals m, such that that estimator will differ from the true mean by this quantity. And this is exactly the same quantity as we had up to a multiplicative constant here for the median of means estimator. So you cannot hope for a better dependence on n, a better dependence on the log of 1 over delta. Okay? And this is a really easy exercise to prove this. Because basically, we just set up two distributions. One that puts both distributions, this p plus and p minus, will put almost all the mass in 0. And p plus puts a little mass on C. And p minus puts a little mass, the same mass on minus C. Okay? Now, you can couple these two distributions such that, and then they will be indistinguishable if all the n samples fall in 0. Okay, so you just work that out and you get this. Okay, you can now set p and c as a function of what m and alpha are. Okay, and you calculate them, and this is what you get. Okay, so this is really easy to see. So this is the best that you can hope for. So this shows the optimality of the median of means estimators, and it also shows that that finite variance is necessary if we want not only a sub-Gaussian tails, but if we want a rate of 1 over square root of n. Okay. So no matter what estimate, it's not only for the empirical mean, but any estimator has to have a rate that is slower than this if the variance doesn't exist. Okay. In fact, in the same paper of Catoni, he showed that that the sample mean is essentially optimal for if you know that you have a Gaussian distribution, then the sample mean is optimal. So even for Gaussians, you cannot do better than this, and you cannot hope anything better than a sub-Gaussian bound. I think even the constant is, yeah. So there's he proves a minimax bound that matches the performance of the. Okay, so it's reasonable to ask for sub-Gaussian tails, because already for Gaussians that's the best thing you can do, and what's nicer than Gaussians? Okay. All right. So the next question is what you already mentioned, is are there estimators that are sub-Gaussian, that have this behavior, but they do not use the knowledge of delta? So we want an estimator that works for all possible confidence levels, or if not all of them, at least for a large range of them. At least down to a minimum delta, which should be as small as possible, hopefully exponentially small in the sample size. Turns out that that's the best that you can hope for. And we would like this to hold for all distributions. So we want an estimator that does not use the knowledge of delta, but has this kind of bound for all deltas in this range. And this L, again, should be a universal constant. Universal or maybe dependent on this class. Okay? It can depend on delta min, yes, though yeah, it won't at the end. Okay? So this is the question. And it turns out that the picture is now more complex. Okay? So the answer is not as clean as before. The median of means estimator really, if the estimator is allowed to depend on delta, then the median of means estimator is really the best you can do. Best you can hope for. But here, if you want estimators that don't depend on delta, then the picture is not so clean. Right? For the median of means estimator, all we needed was a finite second moment, and that's it. Okay, and then everything worked perfectly. Here, here's the picture, or part of the picture. So consider the class of all distributions such that the variance is bounded between two known constants. Okay? Or not necessarily constants. So this can change with n, but two known values. Okay? So suppose that we know something about the variance, and this number r will play a crucial role here. Okay? So r is the ratio of the upper and the lower bounds. Okay? So the larger r is the less we know about the variance. Okay? So let's say that we want to estimate the mean of a random variable, and we know, or we assume, that it belongs to this class. Okay? So here's a theorem. So if this R is bounded, so if we have good knowledge about the value of the variance, then everything is rosy. There exists a multiple delta sub-Gaussian estimator. Okay, so we call these multiple delta sub-Gaussian estimators the estimators that do not use the knowledge of delta. So there exists a multiple delta sub-Gaussian estimator with this delta, okay, which is exponentially small. Right? However, if R is unbounded, then we are really doomed. Then we are in a really bad situation. There is no such estimator for any constant and for any lambda delta min that goes to 0. Okay? So in that case, delta min has to be bounded away from 0, which is really bad. Okay? So there's really a sharp distinction in here between these two. Okay? You see, even if you take Bernoulli distribution, okay? All Bernoulli distributions, so these are really nicely bounded. This is infinite, this ratio. Okay? So you're dead. There are no sub-Gaussian estimators. Okay? However, if we have a bound for the variance, then we do have sub-Gaussian estimators. Okay? And if you think about it, you can see intuitively what's the problem. If P is really, really small, P scales like the variance in the case of Bernoulli distributions. By the way, we proved this using Poissons, but that's somehow the idea. If that P is really small, then you can't really tell the difference between if P is 1 over n or 1 over 100 times n, and then you're dead. Okay. So somehow it's more interesting to the positive side is more interesting. What can we do if the variances are bounded between two values? So here's what we do. This is reminiscent to what's known as Levsky's method in some way. That's a popular method in non-parametric statistics for finding adaptive estimators. So here's what we do. We take we construct the median of means estimators, but this construction actually needs not only estimators, but it needs confidence bounds. Okay, confidence bounds that are of the right order. Okay, and this is where the knowledge of sigma 2 and the boundedness will be used. Okay, so we will for each delta in this exponential ladder, we construct a different estimate. Okay, not only a different estimate, a different interval. Okay, so if delta is very small, then we will have a smaller interval, right? So for delta equals 1/2, this is the interval we get. For delta equals 1/4, we get something bigger, and then we get something bigger, and then we get something bigger. Okay, so we have this sequence of intervals. These are our confidence intervals, and now we look at the smallest k, such that the intersection of all these guys is non-empty from there on. Okay, maybe the first few guys are here. Okay, so this is going to be our k. This is the smallest k such that the intersection is non-empty, and then I will just take the midpoint of this intersection. That's going to be our estimate. Okay? Yes?
Sorry, so I thought I heard someone ask whether or not the estimator depends on delta min, and I thought you said it ended up not depending on it. So, but this looks like
it does. The estimator does. Yes. Then yeah, sorry, you're right. Okay. Scandalous behavior. Okay. So take the midpoint. Okay. So take the smallest k and take the midpoint of that interval. All right. Okay. So here's the proof why this works. Okay. So the key is, of course, that now we are able to find confidence intervals whose length is the right thing, right? The length for each delta is going to be something like sigma times log 1/delta divided by n. Okay, so that's going to be the length of each interval. Okay, that's our assumption, and then we will check that for various cases. Okay, but if we have that and we pick our estimate like this, then it's going to work because of the following really simple reason. For any k, for any level, the probability that our final estimate, this guy that we found, is more than the length of that interval away from the true mean, is bounded by the probability that there exists a j which is larger than k, that is not. There exists a j up there, okay, such that mu is not in that interval. Okay, and this is simply because if mu was in this interval, it was in all of these intervals, okay, then in particular it would mean that this interval was non-empty. But if this interval is non-empty, then by construction our estimate must be in that interval. Okay, so that's why this must be less than that. Okay, but now we can just use the union bound, right? The probability that there exists a j that's larger than that, such that mu is not in that interval, is bounded by the sum of those probabilities, and since these probabilities are exponentially decreasing, this is just 2 times 2 to the minus k. Okay, which is delta min.
So your constant overall is going to be 2√2.
Yes. Okay. All right. So and then I'm claiming, and then I'm not explaining why, but we can construct such a for this particular class we can just construct such these intervals. Okay. That is not hard to see. That you have to work it out. So now we can use this the same technique for other classes of distributions. Okay, not only for the classes of distributions that have a second moment such that the finite second moment, we did the additional assumption that the variance is bounded between two values, but maybe if we don't know anything about the variance, but we have something else, we have some higher moment assumption, then we can still do it. Okay? So if we have a 2 plus epsilons moment, so this alpha can be anything that's larger than 2, and we can look at the class of all those distributions whose alpha's moment is bounded by the appropriate alpha's moment of sigma, and there's this other parameter eta here. Then there exists a constant which depends on this alpha and this eta, such that there exists a multiple delta estimator for delta min that's e to the minus n times n divided by this constant c. Okay? So the delta min will depend on, so if we have higher moments, if alpha is 3, then this c is going to be a constant. Okay, so that's not. But as alpha gets close to 2, then the c will grow, and our delta min is growing up. Okay, and the same dependence on eta. Okay, so the more stringent your estimator is, this delta min will suffer. Okay, and this is true not for all n, but for sufficiently large n. And this sufficient, what that means, that can be worked out explicitly. Because this whole thing follows from this general statement. So call a distribution k regular if for all j's that are at least k, both of these probabilities. So now I take the probability that the average of the first j random variables is less than mu, okay, and I take the probability that the average of the first j is greater than mu, and I want these guys to be not too far from 1/2. Okay, all right. So if you see, if you have this third moment assumption, then if j is large enough, then this will be guaranteed by Berry-Yassine. But for example, if you have a symmetric distribution, then this is already true for j equals 1. Okay? If you have a symmetric distribution or almost symmetric distribution, if the median is not too far from the expected value in this precise sense, then we're fine. Okay? And then for this class, we can construct a multiple delta estimator where the constant depends on this k. Okay? Is from what value of k we have this k regularity. Okay, so if k is, if we need to take the average of many xi such that the mean and the median are close, then this delta min will have to be larger. Okay, but if we have an almost symmetric distribution, then this is going to be exponentially small. Okay. Okay, so any questions here? Because this ends the part about estimating the mean of a single random variable. Okay, so what we've seen is that yes, it is possible to construct sub-Gaussian estimators. Okay, it's definitely possible if the estimator is allowed to depend on delta on the confidence level. The median of means estimator does it, for example. But if we want delta independent estimators, then we need some kind of extra assumption. So just finiteness of the second moment is not enough. We either need some higher moment assumption or some kind of symmetry assumption, or we need to know something about the variance. Okay, and then this is all possible. Okay, so that's for scalar random variables. Okay, I guess 5. Okay, let me give you a little introduction, and then we will continue after the break of what happens in higher dimension. Okay, so now we have a random vector, and taking values in a d-dimensional space. Okay, and it has, I'm not assuming anything except that it has a finite mean and finite covariance matrix. Okay. All right. So this is really the general setup. And now we have an IID sample, and we want to estimate not the spectrum of the covariance matrix as in this morning, but just the mean. This is a really modest goal. Okay? But we want sub-Gaussian performance. Okay? So what's sub-Gaussian performance? What does it mean in high dimension? Well, to say what it is, let's look at the Gaussian case. And in the Gaussian case, the natural estimate is still the sample mean. Okay? So let's look at the performance of the sample mean. This is very classical. The tail, the performance. So now we're going to concentrate on the Euclidean norm. Okay, so the distance between the estimator and the true value, and the sample mean. If the underlying distribution is multivariate normal, then with probability at least 1 minus delta, there's a deterministic term that depends on the trace of the covariance matrix. Okay, so this is the square root of the trace divided by n. Plus, we have another term which depends on the norm of the covariance matrix. Right? The largest eigenvalue, lambda max, is the largest eigenvalue of the covariance matrix. Okay. And this is a nice sub-Gaussian term. So there's a deterministic term, and then there's a delta-dependent term. But somehow this lambda max is typically, if for example, if we have a spherical normal, then this lambda max is just the trace divided by d. Okay. So this is somehow of smaller order than the first term. Okay. So this is what we get for Gaussians. And now the question is, can we replicate this? Do there exist estimators that get something like this? But now for all distributions with the second moment, with all distributions with the finite covariance matrix, let's say allowing the estimator to depend on delta. Can this be generalized? Okay. So one obvious attempt is, okay, let's look at let's estimate the mean of each component. Okay, and you can do that, and then you get something which is not completely trivial, which is kind of nice. We get the trace here. We get the square root of log 1 over delta. Well, the dimension comes in here, which is explicitly, which is not so nice, right? This is a dimension-free result here. It only depends. This is true in a Hilbert space as well. The dimension doesn't even have to be finite for this result. But here, of course, if you do it coordinate-wise, then we have to do a union bound, and then this is what we get. Okay. Of course, with probability at least 1 minus delta. So we just use the median of means estimator in each component. But we can do better, so we will forget this. And so there are at least these 2 papers that were written on this kind of extensions. Sue and Sabato, they were more interested in linear regression, and Minsker set up a general framework. So they both of these papers extend the median of means idea for more general spaces. So Sue and Sabato, they set it up in a general metric space, but Minsker sets it up in a Banach space. Okay? But in this particular case, you can define the multivariate median. There are lots of definitions for a multivariate median, but one natural definition is you take let's take the vector y that minimizes the sum of the Euclidean distances to the points. Okay? So if you use this notion of a multivariate median, and then you do exactly what we did before. So we chop up the data into chunks, into blocks. In each one of them, we calculate the sample mean. And now take this multivariate median. Then you get this very nice dimension-free bound with probability at least 1 minus delta. The Euclidean distance of of this estimator, and the true mean is bounded by square root of the trace times log 1 over delta over n. Okay? So this is very nice because it doesn't use any further assumption on the distribution, on the knowledge of the distribution. It's just like the median of means. Computationally feasible, let's say. This is a convex optimization problem. It's not, of course, it's not as easy as calculating just a mean, but still computable in polynomial time. It's almost sub-Gaussian, but not quite. Okay? It's not really of this form. Right? It's not really of this form because basically this lambda max is replaced by the trace here. Okay? So it's not what we call sub-Gaussian, but again it's very nice because it's dimension free.